Good morning, everybody. This is Rama Krishna from Kale University, dealing with a series of lectures on heat transfer. Today, we will take up a special topic on variable thermal conductivity and also how to calculate the conduction heat transfer if the area of cross section is varying. This topic belongs to one-dimensional steady-state heat conduction without internal heat generation. At the end of this session, the student will be able to understand what is the effect of temperature on thermal conductivity of different substances, and how do you evaluate the heat transfer by considering variable thermal conductivity, and how will be the temperature profile in a slab with variable thermal conductivity, and how to solve the one-dimensional conduction heat transfer problems when the cross-sectional area is varying. We have seen already in the fundamental chapter on conduction, first class I think in the lesson 1, the thermal conductivity of the substance is a function of temperature. Thermal conductivity of metals decreases with increase in temperature, and thermal conductivity of non-metals increases with increase in temperature. And the property, thermal conductivity of a material in solids is due to two important factors. One is free electron motion, and the second one is lattice structure vibration. In metals, with increase in temperature, the number of free electrons remains same. Lattice structure vibration increases, which will arrest the motion of free electrons, thereby the overall thermal conductivity drops. In non-metals, the conduction is purely because of lattice structure vibration, and there is no free electron motion. Hence, with increase in temperature, lattice structure vibration increases, so metal thermal conductivity increases. In case of liquids and gases, conduction phenomena is due to diffusion of gas molecules or liquid molecules. Hence, in liquids and gases, with increase in thermal temperature, thermal conductivity also increases. Let us see variable thermal conductivity. Till now in the problems we have taken, for all the metals or even non-metals, we have considered only a constant value of thermal conductivity. Maybe 0.13 watt per meter Kelvin for rubber, or 400 watts per meter Kelvin for copper, 24 watts per meter Kelvin for steel. Even though the plate is subjected to different temperatures, even though the interface layers are subjected to different temperatures, we assume constant thermal conductivity. But thermal conductivity of the materials is a function of temperature. So when it is considered as a function of temperature, how it is going to affect the solution of conduction heat transfer? Let us see now. Now have a look at this figure. For metals, as I said, with increase in temperature, the thermal conductivity goes on decreases. For example, copper, from 420 it drops. 260 it drops. For magnesium from 180 it drops, and similarly for mercury also. And for non-metals or fire clay brick, the thermal conductivity increases with increase in temperature. You can see here all these graphs are having positive slope, whereas the graphs for metals is with negative slope. And some other metals, non-metals, if you consider, like insulating materials, ceramic, mineral wool, glass fiber, asbestos, calcium silicate, etc. You can observe in this, the dashed line is for still air. Air, when it is at rest, when there is no motion of molecules, it will pass heat transfer from one to the other only by means of conduction. See, the conductivity of the air is very poor. It is much less than glass fiber or asbestos or mineral wool or ceramic fiber. So that is the reason why we always consider the still air as a best insulator. But carefully follow, if the air molecules are in motion, they start convecting heat. The convective transfer coefficient is again in the order of 10 to 50 watts per meter square Kelvin. So it may again affect the heat transfer. So when you have a still air, like entrapped air, either between two window panes or between when you join two different materials like thermal contact resistance, this still air acts. Now liquids, if you see, the thermal conductivity of the liquids also decreases with increase in temperature. So exception is glycerin, which increases. This is a very peculiar phenomena for water. You can see the water thermal conductivity with increase in temperature first increases and then it will start decreasing. For other liquids, thermal conductivity decreases with increase in temperature. Gases. For all the gases, the thermal conductivity increases with increase in temperature. You can see here, carbon dioxide and freon 12 are exhibiting much more lower thermal conductivity than air. So some of the gases again shows positive slope, which indicates that thermal conductivity of gases is a function of temperature, and it increases with increase in temperature. Now let us come to the analytical part of it. So as we have seen from these graphs, thermal conductivity of the most materials varies with respect to temperature. And for metals, K value decreases with increase in temperature. And for non-metals, insulators, K value increases with increase in temperature. Although this variation is non-linear, it is reasonable to assume the variation linear over a limited short range of temperature. You can observe that over a period, maybe between these two linear, maybe between these two temperatures linear, straight line, here straight line, here also straight line. Assuming like that, you can treat it as linear, and the governing equation is K equal to K naught into 1 plus or minus alpha T, where K naught is thermal conductivity at 0 degree centigrade, be careful, and alpha is the temperature coefficient of thermal conductivity and T is the temperature. So at 0 degrees centigrade, this term becomes 0 and you will get K equal to K naught. And for other temperatures, you substitute it, you will get the value of K. So therefore, in this equation, K equal to K naught into 1 plus or minus alpha T, alpha is one unknown and of course K naught is another unknown. So if you have two data points, that means what is the thermal conductivity at two different temperatures, if you know, you can find out K naught and alpha, which will give a complete insight into the variation of thermal conductivity of that particular material as a function of temperature. If you consider thermal conductivity as constant, the temperature variation in the slab is linear, straight line, like this, inclined straight line. If you consider the thermal conductivity, K is K naught into 1 plus alpha T, like in non-metals and gases, the temperature variation will be convex in shape, like this, curved shape. If you consider metals and liquids, where you have K equal to K naught into 1 minus alpha T, the temperature variation is concave in nature. Very important, because you will see that you will get a expression, quadratic expression for this. And we know the Fourier law of conduction, one-dimensional heat transfer problem. It says Q equal to minus Ka dt by dx, temperature gradient in x direction. Where K is equal to K naught into 1 plus or minus alpha T A dt by dx. Take this area to the other side, it becomes heat flux equal to minus K naught into 1 plus or minus alpha T dt by dx. Take dx to the left hand side, Q dx equal to minus K naught into 1 plus or minus alpha T dt. Integrate it both sides. X varies from x1 to x2, that is x2 minus x1, thickness of the slab, and temperature varies from T1 to T2. So K naught is a constant. 1 into dt, integration is T, plus or minus alpha T dt, integration is alpha T square by 2, limits 1 to 2, and Q into dx, integration is Qx, limits 1 to 2. So it is Q into x2 minus x1 equal to minus K naught into T2 minus T1 plus or minus alpha T2 square minus T1 square by 2. From these two terms, let us take common T2 minus T1. You will get Q is equal to, you can see here, Q is equal to, this x2 minus x1 comes to the denominator, and T2 minus T1 common, 1 plus or minus alpha, this becomes T2 plus T1 by 2. That is what written here. Q equal to minus K naught T2 minus T1 divided by x2 minus x1 into 1 plus or minus alpha into T1 plus T2 by 2. This T1 plus T2 by 2 is known as mean temperature. So Q equal to minus K naught 1 plus or minus alpha Tm T2 minus T1 by x2 minus x1 is L. So you can write capital Q is equal to minus K naught into 1 plus or minus alpha Tm is K mean. How? I will explain. K equal to K naught into 1 plus or minus alpha T. What is K1? K naught into 1 plus or minus alpha T1. What is K2? At temperature T2. K naught into 1 plus or minus alpha T2. What is K5? K naught into 1 plus or minus alpha T5. What is K mean? K naught into 1 plus or minus alpha T mean. That is what is written here. K naught into 1 plus or minus alpha T mean is K mean into area, because I have taken capital Q, T2 minus T1 by L. So this is the formula to determine the rate of heat transfer by means of conduction with considering conductivity variation with respect to temperature. So instead of taking K, we have to take mean thermal conductivity of the material at temperatures T1 and T2. This can also be written as Q into K naught A, of course A because small q is converted into total heat, T2 minus T1, 1 plus or minus alpha, T mean is T1 plus T2 by 2. So this alpha into T1 plus T2 by 2 is considered as correction factor to compensate variable thermal conductivity. 1 plus or minus correction factor. So Q equal to K naught A delta T by L into 1 plus correction factor. If alpha is 0, you are not considering any variation. Correction factor will become 0. You will get original world equation. Now let us see a problem. A refractory material of 10 mm thick is maintained at 120 degrees on its lateral surfaces. Thermal conductivity of the slab is given by K equal to K naught into 1 plus alpha T. Because it is a refractory material, insulating material, thermal conductivity increases with increase in temperature, so plus sign is given. K naught is 10 watt per meter Kelvin, alpha is 25. Calculate the heat dissipation through the slab. So the formula for Q, heat flux, is K naught into T2 minus T1, minus sign goes inside, T1 minus T2 by L into 1 plus correction factor. And the correction factor formula is alpha into T1 plus T2 by 2. You know alpha, you know T1 plus T2 by 2, you will get correction factor 0.015. Substitute, you will get the value of Q, 8.12 into 10 to the power 4 watt per meter square. Let us see another problem. A furnace wall of 20 centimeter thick has its two surfaces maintained at 850. Thermal conductivity of the wall is 800 degrees centigrade. At 800 degrees is 1.213 and at 50 degrees centigrade is 0.8. Calculate the rate of heat flow per unit area. Assume K equal to K naught 1 plus or minus alpha T. That's all. So the formula Q is minus K mean A T2 minus T1 by L. See here, the thermal conductivity is given at 800 and thermal conductivity is given at 50 degrees. So we know the thermal conductivity at 800 and at 50. So we want to find the mean thermal conductivity, which is at T1 plus T2 by 2, nothing but K1 plus K2 by 2. So K mean is 1.213 plus 0.82 by 2, 1.0165. Now Q is equal to minus K mean A T2 minus T1 by L, or Q by A is K mean 1.0165 into delta T by L. You will get 3811.87 watt per meter square. See, the important thing here we have to note is when thermal conductivity is varying linearly with respect to temperature, the thermal conductivity at mean temperature is nothing but the mean value of K at temperature T1 and T2. That principle we have used in solving this problem in an easier way rather than calculating the correction factor and then substituting, finding K naught alpha, etc. Because we know the values of thermal conductivities at T1 and T2, directly I found the mean thermal conductivity, I substituted the mean thermal conductivity in the equation and got the heat transfer. This is a very important problem. Third problem, carefully follow. A composite slab consists of two materials with variable thermal conductivities. Material 1 and material 2, K1, K2s are given. Find the steady state heat flux and the interface temperature when both phases are maintained at 600 and 300 degrees as shown below. See, this phase is at 600, this phase is at 300. This is the temperature gradient. Heat is flowing, of course, perpendicular to the flow wall. Now one plate is 5 centimeter thick, another plate is 10 centimeter thick. You know the K1 and K2. K1 is thermal conductivity of first material. It is given in the form of K0 into 1 plus alpha T, which indicates that the thermal conductivity of this is not constant, varying from T1 to T2. But we know only T1 as 600. We don't know T2. Similarly, thermal conductivity of the second material is given in the form of K0 into 1 plus alpha T. So, thermal conductivity of the second material also varies with respect to temperature. We know only T3, we don't know T2. So, without knowing T2, you cannot determine average values. So, what to do? Carefully follow. The formula for K mean 1 is K01 into 1 plus or minus, here 1 plus alpha 1 into T1 plus T2 by 2. This is K0 0.05, 1 plus 0.0065 into mean temperature, T mean, T1 plus T2 by 2. Similarly, mean thermal conductivity of material 2 is 0.04 K0 into 1 plus alpha. In the place of T, you have to take mean temperature. The mean temperature of T2 and T3, that is T2 plus T3 by 2, you will get it K mean at 2. Now Q is equal to the rate of heat flux through this wall is the heat flowing through the first material and then heat flowing through the second material by law of conservation of energy is same. Whatever amount of heat passes through the first layer has to pass through the second layer and then enters into the environment. So heat transfer through the first layer is T1 minus T2 by resistance of this L1 by K mean 1. Of course, A is taken out already. Per unit area we are considering. And the resistance of the second layer is L2 thickness of this by K mean of thermal conductivity, mean thermal conductivity of two material into area. Of course, area is brought here. So by substituting T1 minus T2 by L1 by K mean 1, this is the formula for K mean 1, and T2 minus T3 by L2 by K mean 2. In this equation, the unknown is T2. So find out, you will get a quadratic expression and solve for it. You will get T2 equal to 523 degrees centigrade. So once you know T2 523 degrees centigrade, then you can determine Q. Q is equal to T1 minus T2 by L1 by Ka, K1, K mean 1 into area 1. So Q is equal to K mean 1 T1 minus T2 by L1. You will get the answer 358 watt per meter square. You can also determine this Q by using the formula K mean 2 into T2 minus T3 by L2 because the same heat has to flow. So that is about the variable thermal conductivity. So in any problem, if thermal conductivity is given as a function of temperature, don't take it as an independent parameter, treat it as a variable with respect to temperature and then keep it within the integration, and after substituting K as a function of temperature, you proceed for integration and do it. Now let us see another variety of problems we face in the heat transfer, particularly the fundamentals of conduction, where the conducting area is continuously varying. For example, consider a truncated cone like this. This is the base of the cone and this is the top of the cone. Lateral surface of the cone is perfectly insulated and bottom of the cone is maintained at T1 and top of the cone is maintained at T2 and T1 is greater than T2. As the lateral surfaces are perfectly insulated, the heat transfer is only in the x direction or along its axis. Since T1 is greater than T2, the heat flow is in positive x direction for this truncated cone whose lateral surfaces are perfectly insulated. Now let us see the equation for conduction heat transfer. Q equal to minus Ka dt by dx. What is the A there in conduction? Area normal to the direction of heat flow. So area normal to the direction of heat flow here is pi by 4 into d1 square. But as we proceed, that pi by 4 d1 square gradually reduces and converts into pi by 4 d2 square. So which area we have to consider in such variable problems? Pi by 4 d1 square or pi by 4 d2 square? What is that we have to take? So since the area is now varying as a function of x, you can't treat area as a constant. You have to keep that area also within the integration on the x side, and then you have to express how the area is varying with respect to x as a functional parameter, and then you have to proceed for integration. That is the difficult issue here. So for that purpose, what I will do is, I will consider an elemental strip having dx thickness at a distance x from the end. Face 1, 1, that is bottom face. Let the diameter of this elemental strip is d. Because the thickness I am assuming here, dx is very, very small, I assume d is the same on both sides of this element having thickness dx. So that is why you have to choose a very, very, very small element of thickness dx, negligibly small. So d won't vary then. Now the cross-sectional area of this elemental strip is pi by 4 d square at this left-hand face, and also on the right-hand face approximately pi by 4 d square. So now heat transfer through the entire cone from bottom face to top face is say Q. The heat transfer passing through this elemental strip is also equal to Q. So we will write the expression for this elemental strip, and then we integrate it over the entire length 0 to L. So for this purpose of getting a relationship how the area is varying as a function of x, we will now consider this entire cone. For this entire cone, the diameter here is d1 and the end diameter is d2, varying over a length of L. So d1 minus d2 by L, the taper angle is included taper angle. d1 minus d2 by L is same for the entire figure, which is also equal to d1 minus d by x. Of course, it is also equal to d minus d2 by this distance L minus x. Now from these two terms, first two terms, you can write d is equal to, or d1 minus d equal to, take this x to the other side, x by L into d1 minus d2. Hence d is equal to d1 minus of x by L into d1 minus d2. Now the area of elemental strip at a distance x is pi by 4 d square, where d is d1 minus x by L into d1 minus d2 whole square. X is variable, whereas d1, d2, L are all constants. So area as a function of x, we have obtained it as pi by 4 d1 minus x by L into d1 minus d2 whole square. Now for the purpose of simplicity, let d1 minus d2 by L is C. Therefore area becomes pi by 4 d1 minus cx whole square. Now applying the Fourier law of conduction, Q equal to minus Ka dt by dx minus K, and area is a function of x, So you can't separate them. So take dx and a together to the left hand side minus k dt. Integration of dt is t, k is a constant. We are assuming it is not a function of temperature. So minus k into t2 minus t1, and this area is pi by 4 d1 minus cx whole square. Now we have to integrate this term. Q is constant throughout the length, 4 by pi is constant, d1 is constant, x and dx are related here. Now to simplify and do the integration in an easy manner, let d1 minus cx is y. Differentiate it. d1 constant 0 minus c dx equal to dy. Now when you change d1 minus cx as y, you have to consider the limits also. At x equal to 0, that is when x is 0, y is d1. You put x 0 here, y becomes d1. When x is L, y is d1 minus CL. So the limits 0 to L now changes from y, d1 to d1 minus CL. That is the important thing. So when the moment you substitute d1 minus 6cx as y, the limits also changes. So d1 to d1 minus CL, 4q by pi minus dy by cy square, because dx is minus dy by c, y square minus kt2 minus t. This is 4q by pi c minus dy by y square minus 1 by y d1 to d1 minus cl, which is equal to minus k t2 minus t1. Well, let me check 1 minute. This is a plus, and here it becomes minus. So dy by cy square so this is dy by cy square and it minus sign now. Minus c dx is dy. Oh, sorry. And now upon integration, it is 4q by pi c minus of 1 by y square. Integration is, it becomes plus 1 by y, and the limits will interchange, d1 minus cl. Now substitute 1 by d1 minus cl minus 1 by d1, you will get minus k t2 minus t1. This I have to change. Okay, now it's all right. So 4q by pi c 1 by d1 minus cl minus of 1 by d1. Already we have defined c1, c is d1 minus d2 by l, so cl becomes d2. So 4ql pi c is d1 minus d2 by l, and 1 by d1 minus cl is d2 by 1 minus d1, etc. You will get q equal to minus k pi d1 d2 t2 minus t1 by 4l. That is minus k root of a1 a2 t2 minus t1 by l, pi by 4 d1 square, pi by 4 d2 square. So therefore, in case of variable cross-sectional area, particularly in case of a truncated cone, the rate of heat transfer when the lateral surfaces are insulated is given by the formula minus k geometric mean area into T2 minus T1 by L. So it is not a fixed rule, because here we are assuming for a truncated cone the lateral surface area is changing as a function of x in a linear way. We obtained this expression. Maybe in the examination some other relationship will be given, maybe parabolic or spandrel or elliptical, etc. for a spandrel, then keeping that functional relationship within the integration, you have to do the integration and obtain the solution. It's one problem. In an electronic circuit, a resistor of variable cross section is connected between 2 points at 80 degrees and 20 degrees. Estimate the maximum permissible Joulean heating if the resistor configuration is frustum of a cone having 20 and 15 mm diameter at its extremes and length of the resistor is 2 cm. Assume K for the resistor 25 watts per meter Kelvin, and if the current passing through it is 1.5 amps, calculate the resistance of the resistor. The assumption what we take in this case is its lateral surface is insulated like this as shown in the figure. Its lateral surface is insulated, one end is 80 and the other one is 20, and the diameter at this point is 20 mm and the diameter at this point is 15 mm. Thermal conductivity is 25 mm. So apply the rule. First let us calculate A1 pi by 4 d1 square and A2 pi by 4 d2 square. Now Q equal to K root A1 A2 into T1 minus T2 by L. We substitute it and we will get the answer as 18 watts. Length of the resistor is given as 2 centimeters, that is in the direction of heat flow. The well L is 2 into 10 power minus 2. So you will get the answer Q equal to 18 watts. And this Q is also equal to I square R, where I is given as 1.5 amps. So that leads to resistance is 8 ohms. So the resistance of the resistor is given as 8 watts. This is what is required here for a variable cross-sectional area. So this is only a model problem to alert you that in conduction also the heat transfer area need not be uniform. So for variable cross-sectional areas also you have to calculate the conduction heat transfer. In that case, how the area is varying with reference to X as a functional relationship AX, you have to consider and substitute to get the correct form of equation. I hope it is clear. So like this, area as a function of X you have to express, and then you have to substitute in this A that functional relationship of A with reference to X. Then proceed for integration. This integration is simple. Maybe intermediate level integration you have to perform and determine the value of Q. Now in the last session or last before session, I have given questions from 17 to 26 and the answers are given here. So if the lateral surface of the rod is insulated, the heat transfer surface area will be the bottom face or top face area, which is equal to pi by 4 d square. If the bottom and top faces are insulated, now the heat transfer area of the rod will be pi dl. In a plane wall, the temperature distribution is straight line during steady state with constant thermal conductivity. We will prove it, of course, when we go to the next sessions also. In a microwave oven, the resistance is negligible, so it is true. The window glass consisting of two 4 mm thick glass pressed tightly against each other probably may have a thermal contact resistance. Therefore, the net rate of heat transfer from two 4 mm thick glass window instead of a single 8 mm thick glass window will be less. Now, convection heat transfer through the wall is expressed as in steady heat transfer rate to the wall and from the wall are equal. Therefore, outer surface which has convection heat transfer coefficient 3 times that of inner surface will experience a small temperature difference. So more the convective heat transfer coefficient, less the resistance, less the resistance, less temperature difference between the surface and the wall. And the new design introduced thermal resistance of another layer. Already there is 2 plus 2, 4 mm aluminum. In between you are inserting one more copper, so therefore total resistance will increase and hence it becomes a poor conductor of heat. And for rough surfaces, the thermal contact resistance will be great because they sit at the interface. On the projections they sit one on the other, so more air gaps will be there, more thermal conductivity. That is why a smooth surface will lead to have a low thermal contact resistance. An interface acts like a very thin layer of insulation, so a significance only for high conducting materials like metals, and it can be ignored for 2 layers of insulation pressed against each other, because thermal conductivity of the insulating material and thermal conductivity of the air almost in the same order, imagine. So you need not consider that small thickness, a thin layer, as an additional resistance. But when you take 2 metals, when compared to the 2 metals thermal conductivity, the interface layer, however small it is, its thermal conductivity being very low, of a different order, we have to consider it. And heat transfer through the voids at interface is by conduction and radiation. So by means of evacuating the air and doing it under vacuum condition, the thermal contact resistance will decrease. In steady state operation, the temperature of solid cylinder or sphere does not change in radial direction unless there is a heat generation. Hence, the answer is no for it. So thank you for attending this session. Hope you have obtained all these answers earlier itself. Anyhow, please verify and get them corrected. Thank you very much. Please go through the textbooks indicated here and do practice, because only by practice you will attain perfection, particularly in analytical subjects like heat transfer. More the problems and more worked out examples and more practice problems you do, more perfection you will get. Please keep on doing some problems after the session is over. And for your guidance, you can refer to any of these 4 textbooks. Thank you very much. Thank you.